Okay, so let's get started. Uh, Everybody, could you see my screen?
Yes.
Yes.
Yeah.
Yes.
You see, today we will start the new chapter, magnetically coupled circuits. This is also very important chapter, and I think you have one lab involved with this chapter, probably experiment number 6 or 7. So today we will be looking a couple of things like self-inductance, mutual inductance, coefficient of coupling. There are varieties of terminology with regard to that magnetically coupled circuits. So we will be looking. Uh, so one of the, before discussing much more, one of the best example of magnetically coupled circuit is the transformer. I think at least you all heard about the transformer, right?
Yes, sir.
Yes. So although we'll be discussing in this class somewhat and in the energy conversion class, we will be discussed extensively. We will spend at least 5-6 classes on the transformer. That is very vital in equipment in electric power network. So for example, everybody see this figure one. I'm discussing much more detail. I'm taking you to the board. Can you see there are two coils? So this is on coil and then right side on coil. And you'd notice there is no physical connection. There is no direct connection. But still, if we apply some voltage on this side, left side, for example, name is VP, it is called primary, then you will get some voltage on the right side, which is called secondary. That's pretty interesting. Therefore, the function of transformer, like to increase the voltage on the other side or to decrease. Accordingly, current can be increased, current can be decreased, or even you can maintain the same voltage. So that is the principle of transformer. So I will discuss detail later this one. So this is that figure one is one of the example of magnetically coupled circuit, meaning that they are not electrically connected. They are coupled, they are connected through the magnetism. That is the meaning. Now, couple of terms here I have written self-inductance, mutual inductance, and coefficient coupling. To understand this, let me take you to the board and then again I am coming back to the slide and then followed by some numerical example. So everybody hold on. Okay. So first of all, everybody, let me first write like self-inductance. Self-inductance. So what does that mean? So for example, you have on coil. This is on coil. And for example, you are applying current. Some current is flowing through that coil. So which is IT. So if you apply that current, then current is flowing through the coil. So therefore, what is the effect? What is the consequence of flowing any current through any coil? There will be flux. So you all know that there will be flux. This is the symbol, flux. Let me write down this short flux. So you all know that. This is flux. So this means this is the consequence or effect of applying any current or flowing any current through a coil. The flux will be produced, which is called that magnetic field. Now, for example, this coil has n number of turns. N. N is called the number of turns. Let me write down. Number of turns. Number of turns mean, for example, you see, this is called one turn. And then if you twist, this is another turn. Again, if you twist, this is another turn. In that way, I have just shown here like few, but in real practice, there can be several hundred turns. And if you increase the number of turns, then there will be much more flux and there will be much more voltage induced. So I'm coming that point later. So at this point, everybody understand that I have drawn a coil. That coil has n number of turns. And we are applying current, of course the AC current, and then that is producing the magnetic field or the magnetic flux. Now, according to Faraday's law, so probably you know this one, Faraday's law of electromagnetic induction. So have you heard this one, Faraday's law of electromagnetic induction from the physics?
Probably.
Yeah, probably right. Yeah. So it is. So I am explaining. So what is that Faraday's law of electromagnetic induction? So once there is a flux and there are a number of turns and current flowing through it, so there will be some voltage develop here. There will be voltage built up across the coil. So what is that amount? So according to Faraday's law, everybody see that V will be proportionate to d phi by dt. Yes. This means voltage buildup or voltage development across this coil is proportionate to rate of change of this flux. So why the rate of change of flux? Because this current is varying, consequently flux is varying. This is alternating in nature. This is sinusoidal in nature. Accordingly, your flux is also changing. That's why, according to Faraday's law of electromagnetic induction, this coil will induce or produce voltage, which is this amount. Now, if I want to omit that proportionality sign, so what I can do, V equal to N d phi by dt. N d phi by dt. Therefore, N is the proportionality constant. And this N actually the number of turns of this coil. So now if I move forward, so let me delete this one. If I move forward from here, what I can write, everybody see, this is my N, but what I can say, d phi by dt, how is flux produced? Why is that phi produced? Because of the application of the current. So what I can say, d phi by dt, I can write d phi by di. This means the change of the flux with respect to current. But it was d phi by dt here. So I can say this one is di by dt. This one is di by dt. So everybody see, then the meaning is the same. Could you follow me what I am doing? So are you understanding this line? You see, this one is V equal to N d phi by dt. But phi is this one. So what is the d phi by dt? Rate of change of flux. But actually flux is changing because the current is changing. If current change, then the flux will change. So that's why here this N is this N. Then I have written d phi by di. This means the change of flux with respect to current. But then here it was d phi by dt. So to make this equal, it is the same. I again multiplied by di by dt. So then you see di cancel, meaning is the same, d phi by dt. Do you understand this thing?
Yes.
Yeah, okay. So then now, what is the definition of inductance? For example, we have a coil. If you have a coil, so what is the meaning of that inductance? What is the definition? So,
When the current cuts the magnetic field.
yeah, right. So therefore, L is N actually d phi by di. Sorry, d phi by di. That is the definition of inductance. It has the N number of turns. So we just say L, but this is the definition, N d phi by di. So therefore here everybody see, there is N d phi by di. So I can say This is your L, and then this one is di by dt. So, and then now you come back. So this means we got V equal to L di by dt. So now you come back your DC circuit knowledge. So what is the voltage expression of V? If you know the current is flowing and you know the L is the inductance, what is the amount of voltage? That was V equal to L di by dt. Like you learned, VL is L di by dt. Right? Can you remember now? So,
Yes.
so this is the origination. Yeah. Maybe at that time you did not take care, but actually this is the thing. This is the theory, or this is the phenomena that happens. So this means we can say V equal to L di by dt. This L is called that self-inductance. This is called the self-inductance. Now, today we are looking magnetically coupled circuits. So here I have only one coil. If I have one more coil just nearby it, then what will happen? So let's have a look that one. So what I am doing, so I'm keeping these things. Let me erase these things first. Okay, I'm erasing all of these things. So now I am going to explain you that mutual inductance. Before it was the self-inductance, now it is the mutual inductance. So in case of the mutual inductance, again, little bit. So I'm assuming that I have another coil. I have another coil. This is one coil and this is another coil. And it has, I'm assuming it has N1 number of turns and this coil has N2 number of turns. But you see, there is no direct connection. Both coils are separated. So then what will happen? So, and you see that I am applying current on this coil. I am applying current only this coil. I am not applying any current on this coil. So then what will happen? So just I gave the name ion T. So I apply current ion T. It has the N number of turns. What will happen? It will cause some flux, definitely. So I will call this one is phi 1, 1. And because there is another coil nearby it, it depends on like what is the distance. If it is too much further, then there will be no reaction. There will be no interaction. Nothing will happen on this coil. But if it is nearby, close by, then what will happen? This flux, the main flux, will cause on flux that will just circulate in that way. It is called phi 1 self flux or the leakage flux. And there will be another sets of flux that will link both. So this one is called, sorry, this one is called phi 1, 2. This means another flux which is linking both coils. So phi 1, 2 is the common flux or the mutual flux, because I want to show you what is the mutual inductance. When there are two coils nearby, then this coil has its inductance L1, this coil has its inductance, separate inductance L2. But then both coils have one common inductance, which is called the mutual inductance. That thing I am going to explain that how it happens. So therefore, once again, and then let me write, and then total flux. So phi 1 is this phi 1, 1 plus this one, phi 1, 2. So this means that everybody say, first I applied current ion T only on this coil. We are not applying any voltage, any current on the right side coil. So because of application of ion T, there are two types of flux. One flux is linking only this coil, which is phi 1, 1. And there is another flux which is linking both coils. That is called the phi 1, 2, or it is called the mutual flux. 1, 2 means coil number 1, coil number 2. That is the linking. Phi 1, 1 means only it is confined to coil 1. Same thing, if you apply the current on this side, if you don't apply current this side, if you apply current right side, then again the same thing will happen. There will be only self flux and there will be one mutual flux. So I am coming on that point. So now the two things. So definitely in the first coil, there will be voltage. For example, that voltage is V1. And because there is common flux or there is on mutual flux phi on 2, that will cause another voltage here on the secondary side for this coil. So that voltage is V2. So now I want to write down the expression of V1 and V2. How does it look like? So therefore, you see, I will be using this one. First, I am writing the left side equation V1. So then what will happen? V1 is proportionate to d phi 1 d phi on by dt. And then, so V1, so I initially assumed that this side has n on number of turns. So you see, n on d phi on by dt. So then accordingly, I am going n on d phi on by d ion and then d ion by dt. So this means V1 is L on d ion by dt. So therefore, this makes sense. You understand. How about the right side? How I can write the equation for the V2? So therefore, that I am writing. So V2 will be, just a moment. Okay. So V2 will be N2, and then what I will be writing? D phi on 2 by dt. See the basic equation. According to Faraday's law of electromagnetic, this is the basic equation for any coil, that V is proportionate to d phi by dt. So now I am writing the right side equation. I am directly writing the second line. It has the number of turns N2. So V2 is N2. Where is the flux? Which flux? This one, which is the common, phi on 2. That phi onto this common flux is causing or developing voltage on this coil. That's why I'm writing d phi on 2 by dt. So now if I go ahead, so what I can say, I can write here d phi on 2 over what was the current? D ion. I mean, who caused this flux? Ion caused this one, because there is no current on this side. So that's why I wrote N2 multiplied by this one. But because I wrote d ion, so then I have to write here d ion by d2. So therefore, let me clean up these things here. Okay. So therefore, what I can say finally, I can say that V2. Now here you see there is one thing. What he will call it? You see, we call it L1. L1 was N on d phi on by dt. That was the L1. But here you see N2 d phi on 2 by d ion. So that is called the mutual inductance. I will give the name M21. M21. And then this one d ion by dt. So V2 is M21 and d ion by dt. This means on the secondary side, on the right side, voltage will build up because of the mutual inductance. That's why it is M21. So M21 is called the mutual inductance of coil 2 with respect to coil 1. You see, uh, it is called the mutual inductance. Mutual inductance of coil 2. Sorry. Coil 2 with respect to coil 1. That is the meaning. That is the meaning of the symbol M21 down here. M21. So mutual inductance of coil 2. That's why the first letter, first number 2 and number 1 with respect to coil 1. Because we are applying the current only on the coil number 1, we are not applying current on, and that current on the coil number 1 causing this mutual inductance. Accordingly, this is called mutual, M21. So therefore, what is our definition of M21? N2 d phi onto over di1. That is the V2. Everybody, could you follow me so far?
Yes.
Yeah. Okay. Then now similarly, now everybody see, now I am cleaning off this thing. And then now I want to apply voltage here. I don't want to, sorry, I want to apply current here. I don't want to apply current here. Then what will happen? So let me erase this one. Yes, I kept it open this side now. Like, let me. So we got that conclusion, and then let me clean out these things. Just keep that conclusion that I got that conclusion. Okay. Okay. So everything is the same. Now everybody see. Now I am applying the current on this coil, which I gave the name I2. So therefore, definitely here the voltage name V2, N to N on that is fine. And this is a V on voltage. Okay, so what will happen? So therefore, how you will write the equation in this case? Because it is, so first of all, let's see. So your V2 is N2 d phi 2. So what will happen? There will be one flux, you see, which you will call this time phi 2, the cell flux or the leakage flux of coil 2, and then there will be phi 21. You see, in the first case, previous case, we gave the name the common flux phi 12. This time we are giving the name of the common flux phi 21, and that phi 21 will cause voltage on this coil. That voltage is VR. And once I applied the current I2, that caused cell flux, which is phi 22. So that's why I'm writing V2 N2 d phi 2 by dt. And then again, accordingly, N2 use it. So actually that d phi 22, why it is coming di2? Because of the application of this current. And then do this thing, di2 by dt. Then the meaning is the same, this one. So this will be cancelled. So therefore this is your L2, definition of L2. L2 dit by dt. So everybody understands? This is the same thing as V on when we applied the current in this side. This makes sense. So L2 is the inductance of this side. Okay, now what will be the equation of this on V on? What you can write here? So V on is, let me see. So I'm writing. So V on will be that N on this side, and then d phi 21 by dt. Right, you should write this out. This phi on mutual flux, which is linking both coil number 2 and coil number 1. So therefore, from here, what you can write? N on, then you should write d phi 21 by, then di2. Look, di2. Because this time I have the current only here. There is no current here. So di2 and then di2 over dt. So that the meaning is the same. So therefore, in this case, you will be telling that N on d phi 21 by dt, this is the mutual inductance M on 2, I will tell. This means mutual inductance of coil 1 with respect to coil 2. Here it was M21 and now I got M12 and then di2 by dt. So therefore this M21 and in this case like M22, those are the mutual inductance. That thing we are looking when there are two coils. And then for these off cases, it is found that actually M21 equal to M12. This is the relationship. This means whatever way you say that M21 or M12, that is the same. Which is that mutual inductance? So therefore you look that when there is only one coil or you are applying current only one side of the coil, either this side or this side, then there is the self flux or self inductance, and then there is on common flux which is causing that mutual inductance. And that mutual inductance is responsible for producing voltage on the other side. When you have the current this side, definitely you are getting voltage. But even though there is no direct electrical connection, but still that is producing voltage on the other side because of the mutual inductance. So therefore this mutual inductance is the relationship between this coil and this coil. That inductance is causing the voltage build up on the other side. Everybody, could you follow me so far?
Yeah.
Yeah. So this means what we are looking the interaction between two coils, assuming that those two coils are placed nearby. There is no direct connection, but there is magnetic connection. Magnetically they are coupled. So that's why in this chapter we are looking, now I am taking you to that slide once again. Yes, that is the thing today we are looking magnetically coupled circuits, meaning that this type of situation. And why we are looking this one, why we are learning? Because in our power network, in our system, we have the transformer. And transformer is the one of the best example of that magnetically coupled circuit. Therefore, now come back couple of the things, and then I will take you to a numerical problem. So self-inductance, it is L. It is the typical inductance of a coil. So you all know. And then what is the mutual inductance? That thing so far we look. It is the ability of one inductor to induce a voltage across a neighboring inductor. Again, this is also measured in Henry H. And since this is the amount M less than or equal to root over L1 and N2. So after a lot of experiment and trial and error, so power engineers have confirmed that this is the relationship. Amount of mutual inductance, which is less than or equal to root over L1 L2. And you know L1 and L2 are the self-inductances of two those adjacent coils. And this is the range of that M, like 0 equal to less than equal to M, less than equals to root over L1 and L2. Now, there is one term, coefficient of coupling. With regard to that magnetic coupling, it is designated by symbol K. What is the meaning of it? It's a measure of the magnetic coupling between two coils. This means there are two coils side by side. There is mutual inductance, but how strong is their connection? How strong is their bonding? What is the amount of bonding or coupling of mutual inductance between those two coils, this coil and that coil? That is called the coefficient coupling K. So what is the definition? K is M over root over L1 and L2. You see? Because this M is less than equal to root over L1 and L2, the ratio of M over root over L1 and L2, that is called that coefficient of coupling. And again, this is the range of K, I mean between 0 and 1. So therefore, and then according to the value of K, if you see the K value is 1, this means M over this one fully equal, those coils are said perfectly coupled. If you see that K value is greater than 0.5, the coils are called tightly coupled. And if you say K value is less than 5, the coils are said to be loosely coupled. So therefore, there are three terms: perfectly coupled, tightly coupled, loosely coupled. I mean, is it perfect bonding or tight bonding or the loose bonding, the loose connection? That is the meaning. Therefore, I think these things will help you to do your lab, one of your lab number 6 probably, or lab number 7. I think magnetically coupled circuits. Have you already done with this one, or still you did not do this lab?
We haven't done that lab yet.
Oh yeah, but probably it is coming. It is coming. So that time you will notice that in that lab description, there is tightly, loosely, perfectly. So therefore today's class will help you a lot to understand that lab ahead of time. So far everybody, could you follow?
Yes.
Okay. Now, based on these things, everybody, what you do, please write down this equation in your pen and paper. This one, K definition. K is m over root over L1 and L2. Just write down this one, everybody. Just this one, coefficient coupling K, m over root over L1, L2. I mean, soon in a numerical problem, you will need this one. Have you all written down?
I have a question.
Sure.
So the process of this calculation, the first thing that we should do, I guess, from what you're telling us, is that we should calculate the inductance of both coils first.
Okay, so soon I am taking you on numerical problem, you see. So for example, calculate the phasor currents I1 and I2 in the circuit of the following figure. So can you see, this will be the circuit. For example, on the left side, there is a voltage 12 at in phasor form. And then you see those are given in phasor form. Now what you have to do, I mean, let me show you another problem. I mean, before solving anything, everybody see, this is another example of magnetically coupled circuit. What here you see, 2.5 Henry, 4 Henry, 5 Henry, Farad, and this is 10 ohm. So at first, you have to convert this one into phasor domain. And after that, you have to apply the equation. So those things, I mean, today's problem I will be discussing with you. Just I told to write down the coefficient of coupling, but because that will be needed, that's why I said. So therefore, in this case, you see, it is given 5 Henry, 5 Henry, 2.5 Henry. But to solve the problem, because there are like on loop, this is other loop, there are separate two loops, you have to write down the loop equation, voltage equation. That time you need the phasor domain, their impedance. So first you have to convert those. But the first problem, you see, this one, the first, calculate the phasor currents I1 and I2. What is the amount of current I1 and what is the amount of current I2? This is the question. So therefore, in this case, that J5 ohm, this is your self-inductance or L1. In this case, that J6 is your self-inductance of right side coil. And can you see on top? J3 ohm is that mutual inductance, M21 or M12. And there is on capacitor here, there is on resistor here. So is this fine? Yeah. So now I will show you that how to solve this one, how to write down the equation and what to do. That thing today I will tell you. Then next time you can solve other problems yourself. Okay, so I told you that. So everybody has written down this one, right? K equal to m root over L1 and L2. So therefore, according to this equation, K, because this is M and L1 and L2, if you know M and L1, L2 value, then you don't need to change into phasor domain or anything. K value can be directly calculated. For example, this coil inductance given, for this coil inductance given, and the mutual inductance is given. Then directly you can calculate M. But to solve the other things, other parameters, current here, then you need to convert the circuit into phasor domain. That thing I am telling. Okay, so therefore everybody see the problem, and then I am showing you the solution, that how to do that thing. So now come back here. Let me zoom in. Okay, now. So again, everybody see, that is my circuit. So I have to, question is find out the current I1 and I2 for this magnetically coupled circuit. So here everybody, and then can you see there is two dotted mark here and dotted mark here. So those are called the dot marking or the polarity marking of coil. So therefore in real practice, every coil has some sort of marking. Sometimes it is indicated by plus sign. So in this case, this is the dot and here it is dot. So therefore I am telling you that how to utilize that dot convention in the equation. So everybody see the left side for coil on, that side. This is the given direction, like clockwise. I2 is also clockwise. So this is voltage source, -2 plus 12, 0. So that's why first I am writing -12, because I1 will go, then this is plus minus, here it is plus minus. So then next see plus ion, this one, minus J4 plus J5. And then I have to consider the mutual inductance. I have to consider the mutual inductance, J3, due to current I2. You see, that is the thing we learned, that mutual inductance due to current of the other coil. So that I am writing I2 J3, and then I have given the minus sign here. Therefore, everybody listen, that mutual voltage, this is called the mutual voltage because that is coming from the mutual inductance. So here everybody say the dotted terminal is here. Therefore, see this one, ion current, it was going and it was entering at the dotted point. This means current ion was entering at the dotted terminal of this coil. In this coil, look, in this current, dotted terminal is here, dot point is here. But you see, because it is clockwise, so current first entering at the non-dotted point. So current is entering and then current is leaving the dotted terminal. So this means two opposite thing. In this case, once again, in this case, ion is entering at the dotted terminal. But in this case, for coil 2, I2 is leaving the dotted terminal. So if it would happen that, for example, everybody see this dot point is here. For coil number 2, this dot would be here. This means I2 would enter the dotted point. So therefore, in that case, both ion and I2 are entering into the dotted point. Then I would put plus sign here. So, I mean, for this mutual inductance term, for mutual voltage, whether it is plus sign or minus sign, that is dependent on the dotted points and the current entering or leaving that dotted point. So therefore, once again, for this coil, ion was entering the dot. But in this case, ion was entering here, non-dotted, and then leaving the dot. Entering and then leaving, it is opposite thing, that's why minus sign. On the other hand, everybody see, for example, for coil on, this dot was here. Just assume that this dot is here. Then what would happen? Ion would be entering non-dotted point and then leaving the dotted point. I2 was entering non-dotted point and leaving the dotted point. That was also the same situation, so it would be plus. Therefore, the plus will be when both currents are entering the dotted points or leaving the dotted points. Then it will be plus sign, otherwise it will be minus sign. Everybody, could you follow me?
Yes.
Yeah. So I think I have to show one more problem, then it will be clear. So at this point, I think you understood, and then in another problem, it will be plus. I have another example, then it will be clear. So at this point, everybody see. Okay, so therefore I'm simplifying from here. Here I got J ion because plus J4 and this one, and then 12 I have taken. This is equation number 1. Now everybody see for coil number 2. For coil number 2, there is no source like that. So what I am doing, this 12 plus J6, that multiplied by I2. And then I have to take into account that mutual inductance due to current ion. So therefore, again, because this current is entering at this point, non-dotted, but again, this current entering and dotted, it is the opposite. So therefore, mutual voltage will have the minus sign. So therefore, that is J3, mutual inductance value, and current will be ion. So I got another equation from there. From here, I am calculating ion. I am dividing by J3. So then I got this one, and I am substituting ion value into this equation. Because your question was to calculate the ion and I2. What is the value of ion and what is the value of I2? That was the question. So therefore, I have two equations and I have two variables, ion and I2. That I am trying to find out. Finally, you see, after calculation, I got I2 2.91 angle 14.04, and then ion I got this one 13.01 angle minus 49.39. So therefore, these are just the calculation, phasor calculation. You understand? The main thing is that writing down the correct equation, this one and this one. And even it is not difficult. Everything is the same that you know, the loop equation, only considering that mutual inductance term. Is it plus sign or minus sign? That is the important thing. So I am showing you another problem. Then it will be clear that how it comes plus or minus. Everybody understand this one, this problem?
How did you simplify I1?
This one, this line.
Yes.
You see first, this is the first equation, and then I transferred this on other side, ion J3. And this
Yeah, next
side,
line. Next line.
and next in this line,
Yes.
you see here, 12 plus J4 divided by J3. I am dividing each term. Therefore, you see J6 over J3, how much? It is 2, right? J6 over J3. And what is this one? 12 over J3. So 12 over 3, 4. And then in the denominator J, I am taking the denominator in the numerator, so minus J. And then I2. I just
I
divided.
got it. Yeah.
You got it? Yeah.
The whole moving the J around messed me up.
Yeah. So therefore 12 over J3, this one is minus J4, and J6 over J3, J cancel, 6 over 3 is 2. And then this I2. And then I am, because my goal is to find out ion on I2. I mean, you might find other way, determinant or different method, matrix method, but what I am doing, ion is this on I2. I am substituting ion value in this equation for this one. Therefore, you see, now J, this J is this J, ion value, this one that I put, minus J3I2, 812. And then you look, I am simplifying. I multiplied and then I simplified. And then I got I2 is 12 over this one. This means 4 minus J1. And then you convert into polar form, and you divide. So this is the result. And also I got the I2, then plug in I2 value here in ion equation, this one. And then you convert into polar form. Yes, I converted that polar form. And then multiplication, this multiplied by this one, and angle will be added minus this. So I mean, this portion is normal, just simple calculation, just algebra and phasor algebra. And then only the key thing is right. As long as you are writing this equation correctly, then the rest of the thing is the same. Only the difference between normal circuit and magnetically circuit, considering that mutual inductance. The rest of the process is the same. Is everybody fine? Could you follow me?
Yes.
Okay, so therefore again you are look therefore regarding that mutual inductance plus minus, and let's like another example, and then I think it will much more clear to you. Okay, everybody see this is another problem, although it is asking different thing, but still it will help you to determine the sign. For the following circuit, determine the coupling coefficient. That coupling coefficient K value. That's why I told you to write down that equation. And also calculate the energy stored in the coupled inductors at time t equal to 1 second if Vt is this one. So in this case, this Vt, this is the expression. This is 10 ohm, 5 Henry. And you see the dot point is here, but dot point is here. In the previous case, you see the dot point was here. One was here, other one here. But in this problem, dot is here. And then that mutual inductance 2.5 Henry. And this is 1 over 16 Farad capacitor. Now, in this case, it says determine the coupling coefficient. This means that K that you can easily do, and calculate the energy stored in the coupled inductors at time t equal to 1 second. So now you all know that inductor, it can store energy, right? This is the equation, half Li square, that you have learned in the circuit 1 class. So because there are two coils, so therefore you see the total instantaneous energy stored in the coupled coils, W, half Ln ion square. This means for this loop, this is your Ln. You have to know what is the current flowing here. You have to find out this one. It is not given. Then this will be energy stored. For this coil, you have to know current I2, and then half L2 I2 square. And you have to take into account the mutual inductance. That one, you see, plus or minus M ion I2. Now, depending on those dot points, sometimes it will be plus and sometimes it could be minus. That's why I have written down plus minus. I mean, this is general formula, general equation. So therefore, you all need to remember this one. There are two coils and then there is mutual inductance. So how to calculate the total energy? That is the equation. So therefore, you know these things, L half Li square. Only this is the new thing, mutual term. So plus or minus M ion multiplied by I2. This current multiplied by this current. So therefore, as you can see that for this problem, I mean, similar to this one, in this case, the question was only find out ion I2. And we calculated ion I2 and then we are done. We did not do anything. We did not need to calculate energy stored. But in this problem, we have to calculate this one. Energy stored at time t equal to 1 second. This means that because this is the equation that we have to apply, use. So I know what is L1, I know what is L2. You can see, you know the M value, this one. You just need to find out ion and I2. That's all. So that thing we will be doing. And then at first we will be calculating coupling coefficient, which is the K. So therefore, so everybody see, first I am calculating K here. So what is the K? K was M over root over L1 and L2. Therefore, see, M was this one, 2.5 Henry directly, 2.5. L1 is 5 Henry. This was 4 Henry. So I got K value 0.56. So therefore, that answer is done. Now what I am doing, you see, first, as I said, we have to convert this circuit into phasor domain. We didn't have any problem with this one. You see, this was already in phasor domain. J, 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 J. But here, this circuit, first we have to convert into phasor domain. So therefore, everybody see, first I am writing this V. This was the expression. V 60 cosine of 40 plus 30 time domain function in phasor domain 60 angle 30. So therefore you see this is the phasor domain circuit. I got 60 30. Now I have to convert this 4 component. What is the omega value? Omega value is 4. Everybody see, cosine of 4t. Therefore, omega is 4. This is the 4. And then what is for 5 Henry? 5 Henry j omega L, so j 4 multiplied by 20. And then convert this on mutual inductance. This I got J10, similarly this for J16 and capacitor 1 over j omega c. So taking the numerator taking the j in the numerator minus j4 ohm. So what will be the frequency domain or phasor domain circuit? This one. We just plug in those numbers here. And then I assume this is the direction of ion and this is the direction of I2. But now there is one dot here and then the dot was here. So everybody, could you follow this one so far?
Yes.
Yeah, here still, still we did not apply the magnetic coupling or the mutual voltage. We did not write equation. From here, I just constructed this circuit. And here I am just showing the calculation that you understand. J omega L, J omega L, J omega C, those things. Just from this one, I am converting into phasor domain or frequency domain. So now everybody see, this is my circuit. So what will be the left side equation? So now see the left side equation, just by looking here, everybody see. This is, I can say, minus 60-30 because minus plus, and then ion 10 plus J20 multiplied by ion, and this one mutual inductance plus J10 into I2. This time it will be plus Y. Everybody see, this is dot here, dot here. Look, ion is entering at the dotted. Similarly, I2 is also entering at the dotted point. In this case, both are entering at the dotted point. So the mutual voltage will be plus. So that's why I see the verify, yes, for coil on, you see, plus J10 I2. So this means 60 at an angle of 30. Look this one, 60 at an angle of 30 equal to 10 plus J20 multiplied by ion. This one, 10 plus J20 multiplied by ion plus J10 I2. That J10 was your mutual inductance, this one. That is mutual inductance. So mutual voltage, mutual inductance multiplied by I2. And why I am putting plus sign once again? Look, ion is entering at the dotted point, but I2 is also entering at the dotted point. Both are entering at the dotted point. So therefore plus will be when both are entering at dotted point or both are leaving at the dotted point. For example, this dot is here and this dot is there. Everybody think that this dot is here and this dot is here. Then what would happen? Ion was leaving the dotted point. Similarly, if this dot would be here, I2 was leaving the dotted point, then still it would be plus. Either both currents are entering at the dotted point or both currents are leaving the dotted points. Then it would be plus sign, otherwise it will be minus sign. So that's why, that's why it is the plus sign here. Now, what is the equation for the coil number 2 or mesh number 2? So therefore everybody say, here there is no source. So minus J4 plus J16 multiplied by I2 and then plus J10 ion. So therefore you see this one. This means I have no voltage source. That's why I am writing 0, I2, those two plus J10. And then again, I have two currents, ion and I2, that I have to find out. And then by solving these two equations, you can get this as ion and this on I2. Everybody, could you follow me?
Yes.
So therefore, at your pen and paper, you see, and then so I got ion and I2. Once I got ion and I2, so I have to convert into time domain. I converted into time domain, but then the question was actual question was calculate the calculate the energy stored. of the two coils. This means I have to use this equation, and then it will be plus sign, because we noticed this current is entering dotted point and I2 was also entering the dot. So it will be plus sign here. So plus M ion and I2 and these things. So accordingly, everybody say at the bottom, at the bottom you say I have plus sign. So E half L on ion square plus half L2 I2 square plus M ion and I2. So that is finally I got 20.73 joule. So now I think you have the class, but for a minute, once I got ion and I2 in polar form, everybody see, in phasor form, then I am writing the time domain function. So you know how to do that. Ion this on cosine of 4t minus this on, because that was my omega was 4. So accordingly, 4t minus this on. Now the question was, calculate the energy stored, you see, at time t equal to 1 second. Because energy stored, this is the instantaneous energy stored equation. So this means you have to find out for a specific time t equal to 1 second. That's why here t value is 1. For ion and I2 current, I am putting t value 1. So this means you are getting cosine of 4 minus this one. But what is the 4? 4 was in radian. Then convert 4 into degree. Therefore, I have written at time t 1 second, 4t is 4 radian, which is 229.2 degree. You convert 4 radian into degree. You should be getting this one. And then for 40, I am putting this one. So finally, I got ion minus 3.389 ampere. And again, I am getting I2 2.824 ampere. So I2 is plus, but ion is minus. And then I am using that energy stored equation. So you see, L on L2, those are the original value. M was, those are the original value in the circuit. Yes, this was M, and this is L on L2, original value. And then after plugging in, finally I got this one, 20.73 joule. So therefore, this is just the calculation equation. Main thing is to get the ion and I2. Therefore, until this point, until phasor point, if you can get correctly ion I2, then rest of the thing easily you can do. Just this is time domain, and for a specific time, find out the magnitude of that current ion and I2, and then use the equation. That's all. Everybody, could you follow?
Yes.
Yes.
So therefore, you see the main thing is, I would say main thing is only that considering this one, the mutual inductance effect. Rest of the things are not difficult, that you already understand something. And these are the common thing, phasor domain, loop equation, you all know that how to write. Only thing is considering that mutual voltage term, plus sign or minus sign. That is only the new thing for you. The rest of the thing is just the calculation. I mean, it's a little long problem, but it's just a matter of calculation. Okay, so therefore I think you have the other class. So I am stopping here for today. And then again, next class, I will be continuing this, and then it will be much more clear to each of you. Does anybody have any